Howdy, this is Ethan Arroyo, part of Section 513 of Chem 117, and this is me and my group's budget project for the fall 2025 semester. In this project, me and my group were tasked with learning more about the mechanical engineering discipline and its diverse applications and relations with chemistry. In this project, we were given 5 deliverables, each spread across multiple due dates, and a boat trip where we got to see our discipline in action in a marine ecosystem. This project involved 2 central questions, one of them being investigate the ways that mechanics interact with water coastal environments, and the other being how chemistry relates to our discipline. We decided that bridges, aquatic vehicle motors, and energy production are all ways that mechanics are involved in marine environments, and oxidation of materials from saline solutions such as salt water uh, also interact with mechanical processes in the water.
Firstly, we came together as a group, seeing as we had similar majors, and we thought on how our major, mechanical engineering, how we could help improve other branches of science such as chemical and ocean life. Then we went on a boat trip where we saw major significant land sites such as the Galveston ports and similar things, and we thought, okay, having seen these landslides, how could we as a group mitigate them, so preventing some tragedies, or how could we preserve some of these landslides, or even how do we improve on them using mechanical engineering. Then we came back and we thought on how we could do stuff. We brainstormed, had many ideas, and then after that, we all came together as a team and consolidated all our ideas into the thesis we're about to present to you. This was a very enlightening experience. It gave us an opportunity to think like actual engineers, to think about how our major, mechanical, could actually influence other parts of science, and how we as people could help benefit society as a whole. So this experience was very enlightening, and it was a good experience overall.
So there were 7 members that were present during our project. This included Christopher Cisneros, who was our team manager, TJ Eribo, who was our team facilitator, Jude Hebert, who was our product manager, me, Andrew Orta, who was our the research facilitator, and then there were Ethan Arroyo, Enoch Poon, and Sreegurunath Siva. The rest of them provided help and assistance wherever they could. Challenges that were present were timing meetings, gathering sources, and linking locations to our overall thesis. Timing meetings was a very pertinent issue. We wanted to make sure that everyone was communicated with, and everyone knew what was going on and where in our itinerary we were during this project. Gathering sources was also another issue. We wanted to make sure that all the sources were solid, were factual, and were peer reviewed. Make sure that there weren't any sort of sources that could have been wrong or could have been disproven in any way. Linking locations to our overall thesis was also important. Make sure that every location provided relevance one way or another to our research and our overall thesis. And our primary focus during this project was how to best deal with corrosive effects on mechanical systems within a marine and coastal environment.
Some of our original theses include the deterioration of mechanical components on boats, maintaining power and structure of ocean bridges, maintaining stability and condition and how it relates to buoyancy, determining strong positions of the usage of tidal turbines, and coastal desalination plants and environmentally friendly disposal of toxic impurities. Our study explores the deterioration of mechanical components and the challenges of maintaining marine and coastal structures exposed to ocean environments, focusing on effective methods for preventing and controlling corrosion to enhance structural durability, safety, and sustainability.
Now for our observed locations. Our first one, the top right image, is of a semi-submersible dock, which is constantly in salt water as it is in Galveston. It is a high suspect for corrosion, rusting, and if it rusts too badly, it will fall apart, and this will be bad for both seacraft that it would service and the environment, as metal's not supposed to be in the environment in this type of quantity. The left image is a concrete shipwreck, the SS Selma. It is it was made from concrete during the World Wars as a substitute for metal. It didn't work really well, and it eventually would sink, and now it has moved into Galveston. And so it is important for not only us but future engineers to keep in mind and build with the correct materials for the correct job or for the job. The bottom right is the Galveston Causeway. It connects. It is one of the just connecting us to the mainland, and it's built into salt water, in near the salt water, so it is high risk of corrosion. And it's important that it was built to withstand that and continue to withstand through the future. There were 2 other locations that we had observed. However, they weren't as relevant to the thesis that we had ended up creating. The top image being the Royal Caribbean Cruise Terminal. It is self-sufficient for energy, electricity, but as it is right next to the water, it still deals with corrosion. However, overall, it was not as important to our thesis, as ours was mostly in water body, in water certain objects, craft, structures. The bottom is of the Valero, Texas City refinery. It uses crude oil to make petroleum products that wouldn't be great if released into the environment. So them being strong against corrosive and environmental events are important for the maintainment of the environment in the local area, but it wasn't as important for the same reason of not being strictly in the water or constantly in or around the water.
So now we are at where is corrosion most prevalent. Corrosion is most damaging in the piping systems, the structural support bases and foundations that lay within the marine environment, ship hulls, pump housings, and valve bodies. But pretty much corrosion can happen anywhere, and it can be significantly damaging if not handled correctly. Things that could increase or accelerate the rate of corrosion are high salinity levels, any sort of mechanical systems that are motive and move frequently, that can increase vulnerability. Gear functionality drives the production of electrical chemical processes and creates crevices and pits, which allows for further damage. However, under specific conditions, any metal can experience corrosive effects. We also have corrosive resistant metals such as austenitic, stainless steel, and high strength aluminum alloys. All of these are said to be corrosion resistant, but all of these can also be affected by it. So anywhere basically that has any sort of marine ecosystem around it, they can be affected by corrosion.
Various environmental and oceanic factors can have effects on corrosion to occur in different ways. One such factor is different corrosion zones, labeled as the atmospheric, splash, tidal, submerged, and subsoil zones. The corrosion that occurs in these zones is a result of an electrochemical process of sea salts acting like electrolytes. The splash zone has the highest rate of corrosion due to high oxygen and chloride content of the recurring splashing water. The tidal, submerged, and subsoil zones have decreasing corrosion rates, respectively, as part of high and low tides, marine growth on the metal, and amount of oxygen in the soil. The rate of corrosion is driven by many factors such as humidity, temperature, and salinity, and time of wetness. As humidity increases, corrosion increases by increasing time of wetness. Higher ambient temperatures can lead to higher ranges of atmospheric corrosion and affect relative humidity and time of wetness. Increase in wind speed means more sea spray and depositing more electrolyte solution onto the metal surface. And finally, an increase in salinity means more chloride ions can penetrate the metal and protective coating faster.
Corrosion is a very serious problem that we have to fight against, and the best way to fight against it is via prevention. For certain metals, such as aluminum and titanium, their alloys can be integrated into metal organic frameworks, MOFs, are hybridized crystalline materials with highly ordered pores and are created through coordination of metal ions with electron-donating organic ligands. MOFs have large surface areas, high porosity, and tunable pore sizes, which make them ideal candidates for a variety of applications, such as usage as catalysts, gas storage, and corrosion control. Certain MOFs, like University of Oslo 66 or UIO 66, are extremely hydrophobic and very stable in water, which will make them very strong in the usage for corrosion protection for surfaces, objects in water. In addition, they can be modified to fit different situations. For example, the materials of Institute Lavoisier 101, MIL 101, incorporates chromium ions in addition to benzene 1 and 4-dicarboxylate, and can be further functionalized with amine groups to improve absorption capacity for carbon dioxide and other corrosive gases.
So to wrap everything up, our boat trip project gave us a clear outlook on how water chemistry changed throughout the trip. We mainly focused on what happened at each stop, which ions increased and decreased, and what those changes told us about the environment at each location. When we compared our observations across the different stages, the patterns made sense. Some were more stable while others showed noticeable shifts of things like pollution sources, mixing, or natural processes. The stars on the pictures, those locations, figure 1, 3, and 4, were the most significant in us understanding that salt water with water is a result of rapid corrosion, leads to rapid corrosion. And metal components, they lose strength and reliability over time when they're closer to this saltwater environment. And reinforced concrete failures show hidden corrosion risks. And all of these findings support our thesis on durability and corrosion prevention. Looking at the whole picture, our main takeaway is that even small changes in the environment or in the surroundings can affect the chemistry of the water as it moves. So understanding these trends really helps explain why the final sample, of these figures, looked the way it did, and why consistent monitoring matters, especially when you're looking at mechanical systems.
To conclude our project, we showed that corrosion is one of the biggest challenges for anything built in a coastal or marine environment. Being constantly exposed to salt water, humidity, and changing weather causes materials, especially metals, to break down much faster than they normally would. On our boat trip, we saw this firsthand on bridges, docks, and old ship structures, and even industrial areas along the water. Understanding the chemistry behind corrosion helped us see why it happens and why it's such a serious issue. Processes like oxidation and electrochemical reactions slowly weaken the metals, which can eventually affect the safety and reliability of the mechanical systems. That's why engineers have to think ahead when designing anything for the coast. Using corrosion-resistant materials, applying protective coatings, and keeping up with the regular maintenance are all crucial steps in preventing long-term damage. Good designs can make a big difference in how well a structure holds up over time. Overall, the main point we learned is that controlling corrosion isn't optional, it's essential. It helps keep marine structures safer, stronger, and able to last much longer in harsh environments.